My name is Arthur Firmino, and today I'll be presenting our work titled Progressive Denoising of Monte Carlo Rendered Images, authored by myself, Jeppe Revall Frisvad², and Henrik van Jensen. Monte Carlo light transport algorithms, such as path tracing, have been ubiquitous since the introduction of the famous rendering equation by James Kaguya in 1986, thanks to their simplicity and ability to render scenes with complex light transport. However, the nature of these algorithms is such that rendered images will contain noise due to the use of Monte Carlo integration. Often, many thousands of samples per pixel are required to reach an acceptable level of noise, and this number is dictated by a 1/square root relation. Despite the advent of powerful hardware dedicated to ray tracing and variance reduction techniques, it is often not computationally feasible to reach an acceptable level of quality by computing more samples, thereby requiring the use of image denoising. Monte Carlo image denoising has been a vital component in the adoption of path tracing in the movie industry. In recent years, denoisers have dramatically improved in quality due to the advent of neural networks and machine learning. Learned denoisers are not necessarily perfect, however, and may suffer from bias that is sufficient to be perceived as a loss of detail and image blurring. This loss of detail can often be seen when comparing denoised and non-denoised images, particularly in the presence of high-frequency details. In this example in particular, the varying specular reflections from the light post's normal map seen in the left image are made smooth and blurred by the image denoiser. Such loss of detail is also observed on the scene's rough wall to the right of the post. The difference can be made clearer by comparing error images of the denoised and non-denoised images. It can be observed from comparing such images that while denoising reduces error almost everywhere in the scene, there are a few spots, such as on the light post again, where the error has actually increased. Plotting the error of denoised and non-denoised images against the number of samples per pixel reveals the decreasing utility of denoisers in reducing error as the sample count increases. If the sample count is high enough, denoising might be counterproductive and decrease the overall image quality, which is undesirable. A simple idea to improve the overall image quality would be to denoise only when it reduces error compared to not denoising. Of course, computing the exact error of a denoised image, as done here, requires first rendering a ground truth or reference image with a very large number of samples per pixel. However, we can use Stein's unbiased risk estimate to compute an estimate of the denoised image error even without knowledge of the reference image. Stein's unbiased risk estimate, also abbreviated as SURE, allows computing an estimate of the squared error of a denoised image, even while treating the denoiser as a black box, which is a suitable treatment for deep learning-based denoisers. SURE has appeared before in computer graphics literature, being used to guide adaptive sampling and for optimizing denoising parameters. The error estimates computed using SURE are of practical accuracy, particularly as the sample count increases, likely due to the distribution of the sample mean approaching a normal distribution. The example shown here shows a near one-to-one correspondence between the actual error computed using the ground truth and the error estimate computed using SURE. Being able to estimate the error of a denoised image, how can we use this to improve the final image quality? Using the same principles involved in the derivation of SURE, we can derive an expression for the optimal per pixel mix parameter between denoised and non-denoised images. While the expression itself is insightful, we cannot directly use it as we can only estimate some of its terms, and there is simply too much variance in our estimates of these terms. One option would be to filter the values of these terms, and this was the approach taken by another recent work titled Ensemble Denoising. In our work, however, we decide instead to lend this task to a neural network. The core idea of our method, as in the previous slide, begins with a rendered image. This rendered image is then denoised, typically using an existing pre-trained denoiser. Our method then takes these two images as input and produces per pixel parameters that are used to mix between the rendered and denoised images. This mix takes the best pixels of each image, and the final output is of higher quality and lower error than either of the inputs. This slide simplifies the pipeline of our work, progressive denoising, into 5 essential steps. The first step consists of denoising the rendered image, typically with a pre-existing denoiser, and computing an error estimate of its output using SURE. In our work, we tested multiple different denoisers, including denoisers with different neural network architectures, such as UNet and kernel predicting neural networks, and found our method worked well when applied to either of them. The denoised and non-denoised images, along with estimates of their per pixel error, computed using SURE and sample variance respectively, are fed as inputs into a neural network. We use a relatively small convolutional neural network, 6 layers deep, with residual skip connections between the layers. The neural network then predicts a per pixel parameter, alpha, with which to mix the denoised and non-denoised. During training, we perform random swaps of the inputs, switching denoised and non-denoised images along with their error estimates. We found this prevented the network from falling into the local optimum of simply returning a value of 1, corresponding to 100% of the denoised image, as this image is nearly always of lower error than the non-denoised image. To ensure the output is consistent in the limit of many samples, we calculate by how much the mixed output deviates from the rendered image by computing the t-statistic of the weighted average of each pixel's neighborhood of pixels. If the absolute value of the t-statistic is found to be large, meaning the predicted value deviates significantly from the rendered value, then the mixing parameter alpha is scaled towards 0, and the final predicted value becomes closer to the rendered value. The t-statistic is adaptive to the level of variance in the rendered image, which tends to 0 as the sample count increases. The necessary deviation for the mixed parameter scaling is initially very large, but shrinks as the sample count increases, ensuring consistency. Finally, the rescaled per pixel parameter alpha is used to mix the denoised and rendered images, and this final image is output. A sample of our results will now be presented. In this recognizable scene, we noted that denoising often overblurred details on the two columns with the rough and bumpy surface in view of direct lighting. On the left, the result of denoising using a high-quality production denoiser, we observe a loss of detail that is subsequently recovered by progressive denoising, shown in the right image. Here we highlight the difference between the images and the ground truth, with red and green indicating negative and positive differences respectively, and brightness corresponding to the magnitude of that difference. Although not clearly visible here, it still makes sense to use denoising in this scene even at over 1024 samples per pixel, as the areas of the image not in direct lighting still contain a large amount of noise. This short clip of the same scene illustrates the progressive nature of our method. With regular denoising on the left, the image quickly stops improving, despite the increasing sample count. With progressive denoising on the right, details are seen fading back into the image as the sample count increases. This landscape scene, containing many small elements and high-frequency details, is a notable challenge for denoisers. The small leaves in the distance, barely a pixel across, often become blurred out with denoising. This is a problem that progressive denoising is well able to address. As shown in these different images, our method significantly improves the denoising qualities of scenes rich in vegetation. This video of the same landscape scene demonstrates our method's improvements. This snippet of our results of the last two scenes further illustrates the progressive nature and consistency of our method as the sample count increases. Progressive denoising addresses the decision problem of whether to denoise at higher sample counts but risk overblurring of details, or to not denoise but risk noise despite a high sample count. By allowing an artist to enable denoising and not having to worry about its limitations at higher sample counts. Our method, of course, works well for a wide variety of scenes. In our test dataset, we use the following 10 scenes, excluded from our training dataset, and we compared our method to an existing popular denoiser. Progressive denoising showed an overall improvement across a variety of error metrics, and these results show that it does not depend on whether the base denoisers use auxiliary features or not. Deep Combiner is a title of related work, which is in some aspects similar to ours. Like our method, Deep Combiner combines estimates from denoised and non-denoised images and uses a neural network to do so. Unlike progressive denoising, which predicts a single mixed parameter per pixel, Deep Combiner predicts a full rank kernel, which is then applied to the residual of the two images. the application of such a kernel incurs additional computational cost compared to our approach. Deep Combiner, while also being able to improve the quality of image denoising, is not consistent and does not guarantee convergence to the ground truth even as the sample count increases. The following error plot clearly illustrates the difference between our method and related work, highlighting our contribution. The result on this slide illustrates how progressive denoising performs on a challenging scene with extremely high variance. The scene, which consists of a bump-mapped specular plane lit by environment lighting, required up to nearly 1 million samples per pixel to converge. We observed that between 10 to the 5 and 10 to the 6 samples, progressive denoising converged slower than the Monte Carlo rendered image, but still improved upon the regularly denoised image. This slide illustrates one of the limitations of our method. At very low sample counts, the t-statistic test, part of our method, sometimes fails due to insufficiently accurate sample variance estimates. Many of these artifacts were mitigated by instead calculating the variance of a weighted average of each pixel's neighborhood. However, it can still be an issue at very low sample counts, such as 2 samples per pixel, as shown in these 2 examples. Our implementation does not specifically address the challenge of denoising with regard to temporal coherency. We briefly investigated how our method performs in this regard by denoising sequences of still images rendered with different random seeds and at sample counts of 32, 256, and 2048 samples per pixel. When compared to the same sequences denoised without progressive denoising, we found no visual improvement in terms of temporal coherency. It thus remains an area of future work to investigate how approaches used to construct temporally coherent denoisers could be combined with the method presented here, and whether the adoption of a temporally coherent denoiser as a base denoiser would be sufficient. To conclude this presentation, progressive denoising is a technique that improves denoising by incorporating it only when it is beneficial over the rendered input. It makes denoising asymptotically unbiased, ensuring convergence to the ground truth as the sample count increases. And it can be used on top of pre-existing high-quality image denoisers, as was done in our experiments.